Hello, my name is Sky Bender-Demal, and I'm going to give a quick introduction to the ndtv package for R. The ndtv package was written by me and the rest of the StatNet team as a way of visualizing the dynamics of longitudinal networks. It works mostly with network objects that have been encoded in the network dynamic package, and so that could be various data sets that people have or the output of Sturgeon simulations from StatNet. The package, I'm going to give this demonstration using RStudio, which provides a nice interface for working with R, the statistical software R. And the first thing we would need to do, of course, is load in the package. So this prints out the citation information for it. And of course, as all R software, if you want more background help, you can use the built-in help to access the manual pages. There's some online tutorials as well. One of the main things that this ndtv package is used for is rendering out animations. And we have an example data object called short Sturgeon sim, which is the output of a Sturgeon simulation, the evolution of a statistical network model. And we can load that into the workspace, and now we can quickly render it as an animation in the R plot window using the render animation command. So this goes through and calculates a bunch of time points for the layout of the network at the various time points, and then renders them and caches it in the background here, and we can replay it with this AnyReplay command, and it'll show the network evolving over time in R's plot window. We can also, there's some other commands provided by the animation package that allow us to save it out as a GIF or an MP4 or other movie formats if you install some additional software. One of the recent things we've added to the package, which I'm really excited about, is the ability to export these animations as HTML5 SVG animations that can be embedded into a web page or shared with other researchers, and even included as our markdown documents. And these are interactive, and so we can render these out with render d3 movie, and again we give it the network object that we want it to render, the short Sturgeon sim, and now it's going to run through and open a web browser with our animation in it, and we can play this animation. We're using the play controls. We can go backwards and forwards in time. We can slide around on the time slider. We can zoom in and out. We can select and highlight elements of the network and watch them move around in time. So it gives a bunch of features that you don't have with just a standard movie. That same command, the render d3 movie command, can also be used. If we change the arguments, it'll render its output as an HTML widget, which means that it can display the animation inside the R plot window here. And if you were to include it in an R markdown document, as I was saying, then it would show up as right in the HTML page. So this, for example, is a vignette for the ndtv D3 functionality, and it has the animations included right in it as the HTML5. So that's a recent feature we've added that's pretty exciting. In addition to animating networks as movies, there's often useful to include static representations of the dynamics, especially if your intended output is a journal or something where you're not going to be able to give people access to an animation on the web. So a common way to do that is a small multiple technique, where you could show a series of static snapshots of the network evolving over time. And we can do that using the film strip command. Film strip, which effectively we take the network. I'm going to tell it not to draw the labels because it's going to make it really small. Display labels equals false. and we grab a series of the snapshots. So here's time 0, time 3, etc., all the way up to time 25, and render each of those frames of the movie out as sort of like a film strip. And we can see the network is connected, has a few isolates, and eventually gets down here and breaks into a couple of different pieces. This shows the evolution of the network in as these sort of bins, but it doesn't allow us to see the overall sort of change in structure at the same time that we're seeing changes in position and time. So a sort of hybrid approach is to use what we call a time prism, which is to stack up these slices of the film strips. And to do that, we're first going to compute the coordinates. This step usually happens invisibly inside the other processes of the network. And then we can render it out using this time prism command. And this is going to give us the sort of classic view people like to play with, showing the network slices at different points in time. So you see the time is on the vertical axis in this view, and we can see it's connected here and then breaks into parts. I find this view to be, it's difficult to use if you have a large or complicated network or a lot of time slices, but it's often useful to sort of as an illustration to help people understand what you mean by the various discrete time slices. Another useful view for debugging and making sure your data set has been loaded in correctly is just a straight timeline view. And this renders a view just of the activity of all of the objects in the network. So these are all the vertices here, and these are all the edges. And the vertices are always active, so they trace out a single line over time from 0 to 25, and each of the edges is active or inactive for various points. You can see edge 5 here is on from 0 to 6, and then it's off, and then it's on again and continues. So this is often helpful to sort of get an overview of the dynamics, but it doesn't show us any of the relational information. You can't tell which edge is connected to which vertice, and you can't tell how close the vertices are to each other in network terms. There is a hybrid view that sort of attempts to show both the changes in proximity and the time information of the vertices, and we call that a proximity timeline. And this example here, we're showing the same network, and each of the lines is tracing out a path for the vertices, and down here we have the isolates, and here's the set of the connected section of the network. And some of the vertices split off and some get drawn into the network. They're positioned on the vertical axis so that edges that are vertices that are tied tend to get pulled closer together. So you can see that as the connected section moves along time, eventually it breaks up into a couple of chunks here. Again, we're using R, so it allows us access to a lot of other features. For example, as always, we can print out the short Sturgeon sim object to get a sort of summary representation of it. So it's saying there's 26 distinct time points, and so it's a discrete time representation, and there are 16 vertices, etc. And we can always convert the representation from this network dynamic object to just a data frame that's representing the activity of all of the edges here. So each edge spell of activity has an onset and a terminus, and which vertices it's connecting together, etc. As I was saying, the package relies on Network Dynamic to provide the underlying data structures. Network Dynamic also gives a bunch of tools for importing and exporting data sets, and we've also recently released the TSNA package, which includes a bunch of utilities for doing standard SNA metrics and some temporal paths and various features which didn't used to be easily available for dynamic networks. Again, this is the NDTV package, a quick introduction to some of the cool new features, and this is released by the StatNet team, and I'm Sky Bender-DeMol.